Saxon Algebra 1, lesson 114. We're going to talk about exponential growth. This is a topic we're going to come back to next year and the year after. So this is just us dipping our toes in the water and getting a feel for it. So this is the first time you'll hear about this and most certainly not the last. Exponential growth is something that we've had a lot of worldwide experience with because it is the model by which the COVID virus was able to spread, right? One person infects 2 people, they infect 4, they infect 8, they infect 16, 32, right? It grows, not just in a straight line, but it grows in a curve that is increasingly steep. And we're going to start to play around with those, but don't worry, we're going to go step by step. The first thing I want to do is teach you how to use the calculator that we will need to evaluate these kinds of problems. All right, so let's start with just figuring it out. The tricky part for me to teach this to you is that my calculator is also my camera and it's being used right now to record this. So what I've done is created a fake oversized calculator on which I can show you the buttons. I want you to get a good app for your phone, your mom's phone, your iPad. You find something online, I'm sure, if you're using a conventional laptop or desktop. But you don't need a graphing calculator. A graphing calculator will have a window at the top, a screen that is capable of producing pictures. You don't need that. We're not going to use a graphing calculator, but it does need to be a scientific calculator that has these buttons on it. I think I'm using an app. If you have any problems finding a good calculator app, let me know. You guys both have older siblings that are doing this. They've figured that out. So if you have any problems, ask them what they use. All right, I want to introduce you to these 2 rows of buttons. This button, x squared, what you do is you take the number that you want to use for x, you enter that, then you hit this button, and it will give you the square. Same for this one, only cubes, right? If you want to find the cube of 4.623, you enter 4.623, hit this, and it'll give you the cube. This one is a little bit different because it allows you to control not just the base, as we did here, but it allows you to control the exponent. So what you do with this is you enter your x, let's say it's 7. We want to do 7 to the 4th power, let's just say. So we enter 7, then we hit this. It will recognize 7 as the value for x, but then it waits for us to give it one more value, and that would be the, what did I say, 4? Up here, right? So we would enter 7, this button, and then 4, right? So you enter the variables in alphabetical order. First put in the base, then this, then that, okay? There's also a row, just beneath it, it should be, of square root buttons that work the same way. Here we can get the square root, here we can get the cube root, here we can control both the base and the degree of root, but we have to enter both values. So we enter the value for x, then we hit this button, and then we enter the value for y, okay? That rule of thumb works for any button that has 2 letters on it. Put in the first one, then hit the button, then enter the second one. All right, so we're gonna be using, I think mostly this one in these problems, but I'll refer to this as we go, all right? So we're supposed to evaluate (1.06) to the 8th. We're raising 1.06 to the 8th power using a calculator. So the way that you do that, this is the function that we'll use, right? Because it looks like that. So we enter 1.06, then this button, then 8. All right? When you do that, you should get 1.593848,075. Now that's a lot of digits. And we will oftentimes round, so you'll have to remember your rounding rules. We'll talk about that as we go, but that's the whole big long string. The book gives you some instructions for how to use a scientific calculator or a graphing calculator, but they're on calculators that are historic at this point, right? Our phone calculators work differently. The process for entering the buttons is different. So don't listen to those. Don't listen to what John says. All right, let's do a problem that actually shows you exponential growth. They're stories, but that's okay. That helps us make sense of it. The number of bacteria in the dish tripled every month. Okay, I'm gonna write that down. So this is some sort of science experiment. Have you ever seen a Petri dish? It's a little round glass dish with a thin layer of clear jelly in it, gelatin, like Jello, and it's got protein in it, and so it's an idea home for bacteria if you're trying to grow them, because it's got nice, delicious chemicals in there that the bacteria can eat and thrive upon. So that's what the dish represents. It's a Petri dish, is what I'm assuming. If there were 2,500 bacteria at first, then how many bacteria were there in 10 months? This is the way these problems will work. They will tell us what we started with, and then they'll tell us the growth rate. Okay, so this is start, and this is the growth rate, and then this is the end. That's the pattern. All of these will finish. What that we'll use. What we need is a formula. And I'll explain this all to you. I just taught the 1/2ers, Joel and Jojo and Alexis. I just taught them the Pythagorean Theorem. And when I wrote it down, this really isn't funny. It's perfectly horrible. I wrote a squared plus b equals c squared. I forgot to write the square on the b. I eventually caught it, but it was after we'd done the problems. Oh my gosh, I probably confused them so badly. So let me see. I went back and fixed it, but good Lord. So let's see if I can get you this correctly. Y to the t. Okay, in this expression, A equals amount, T equals time. So A to the 0 equals the starting amount, and A to the T equals the amount after time T, right? So if it's 6 months or 8 weeks or whatever, that's the number we use. And then Y equals what we call the growth multiplier. And that's like the growth rate, same difference. Multiplier or rate. Okay, you'll see that both of those words are used in different scenarios. So this is our formula, and I'm going to include the definitions with it, because if you don't know what the letters mean, it doesn't do much good, does it? All right, so take a minute and get that settled in your notebook. I know you're still writing your formulas in your notebook, because why wouldn't you? And then we will go ahead with our bacteria in our dish problem, because I know you're dying to know, right? First of all, who would count 2,500 bacteria? That seems very difficult. 2, it seems like a really perfect number, right? I wouldn't think the bacteria would necessarily come out in round numbers. And 3, there's going to be a lot more at the end of 10 months. Who is going to count all those? That's what I want to know. All right. So what we're going to do is we're going to take the information we know and we're going to plug it in here. In our situation, the starting amount is 2,500. So that is what our A to the O is, right? our time is this. I'm going to say t equals 10. A to the O is 2,500, right? I can write it in so it's super clear. And then our growth rate, y equals 3. Because it triples every month. So triples means 3, right? Okay, so now all we have to do is plug this in. The amount that we're trying to find is the amount after 10 months, right? That equals the original amount, 2,500, times the multiplier raised to the power of whatever the time is. Okay? So now, grab your calculator. If you don't have it handy, pause me and go get it. If you are going to use a calculator on the same device that you're watching me on, that's fine. Just pause me and try it. What we're going to do is we're going to work backwards through this calculation. We're going to use this key to simplify this first. So we'll hit 3, this function, then enter 10. You should get a nice, juicy big number, and then you're going to multiply that number by 2,500. Pause me now if you need a minute to work on that, because I'm going to tell you the answer. It'll become... You don't necessarily have to write this down. When we're working in calculators, I want you to hold the calculation in the calculator as much as possible. So you should get 3 to the 10th should equal that. And then just keep that right in your calculator and multiply it by 2,500. And the final number you should get is, it's a big number. And it comes to you, hopefully, in scientific notation. 1.4762 times 10 to the 8th. So let's figure out what that number would be. 14762. Our decimals here, we need to move it 8 places. 1, 2, 3, 4, 5, 6, 7, 8. Fill in with zeros and put in some commas. 147,620,000 even. That's a lot of bacteria. And I don't want to be the one who smells it. That's the right answer. Okay? If you have any problems running these numbers through the calculator and getting them to behave, let me know. Ask your sisters, honestly. They can help you, or let me know in the video chat, all right? Okay, let's do another one. This one uses money in the bank rather than bacteria in the dish. And I'm going to write our formula again up here. Okay, James deposited $500 at 7% interest, compounded annually. I don't know if you'll remember, we did a lesson in this last year in the Algebra 1/2 book. Compounded annually means you get paid interest on your interest. It's what's normal. Okay, how much money did he have after 14 years? Okay, so that tells us the original amount is $500. The rate is the same as the growth rate, and the growth multiplier are the same thing. This is 7%, so that's 0.07, right? That's 7%. And then t equals 14. And once again, John wants us to find out how much money we would have left after 14 years. Again, compounded annually is the way this is set up to work. So we don't have to, that doesn't do anything weird, complicate our situation at all. All right, so let's plug in. The amount after 14 years is going to equal the original amount, 500, times the multiplier, 0.07, raised to the power of time, 14. That's going to be a big number, isn't it? So, we enter, again, we start at this end of the calculation. That's not a hard and fast rule, but it's a pretty standard rule of thumb that when we're calculating, we work backwards through the expression as we've written it. So I'm going to start here. I'm going to use this button again. So I'm going to enter 0.07, hit this function key, and then enter 14. That will give us a nice big number, and then we multiply that by 500, and we should get we will get 789, sorry, ignore that, 0.27. I wish I would have checked that because I want to make sure, okay? That will be how much interest, okay? Because we multiplied it by a rate that reflected the interest rate. If we want to know how much total money he would have in the bank, we would have to adjust that rate like so. This is to find the interest only. And we can tell because that's the interest rate. If we want to find the total amount he'll have in the bank, then we have to change it like this. 1 plus 0.07 to the 14th. Because he's going to still have the $500 in the bank and be earning interest on, he still has the $500 in the bank, and then he'll be adding the 7% over 14 years. So this one is how we account for the original deposit. And the 7% is the interest only. The question, John wants to know both, by the way, in this case. So first we found the interest only because in our multiplier, we just put the rate of interest. When we go to find the total amount, we add a 1 here to include the original deposit. When you multiply that out using your calculator, again, this time it will be 1.07, function key 14. The amount that we will get is $1,289.27. Okay, so that's the total amount that we'll have in the bank. Or not us, it's not our money. Who is this dude? It's James. Okay, and what's cool is we can compare these amounts, right? 1289.27, 789.27. If we subtract them, we get $500. And that's the amount of the original deposit. Okay? So another way to work this problem would be to calculate the total amount first using 1 plus the rate, that. And then if we wanted to find the interest portion of it, we could just subtract, right? We could have taken this minus the 500, and that would have gotten us the interest portion without having to run as many complicated numbers, okay? I wanted to do it the longer way just to get you more used to those calculations. Okay. There are 2 lovely exponential growth problems for you to contemplate. We are not going to do part C of this problem, and I will tell you why. Part C involves using a graphing calculator, the kind that has that window, that little screen built in there, and can draw, delightfully primitive pictures of graphs, right? Here's an exponential function. Here's the reason why I don't like to use graphing calculators in high school. Because once, it happens to me too, you guys, it's just part of human nature. once we get this tool in our hands with all these buttons and bells and whistles, especially pictures, we forget about the math that we're doing. We forget about what the calculations look like, and our brains are just reduced to punching numbers. And I can prove it to you. That's what I had to do with this, right? We were just talking about punching numbers. What keys do you use? What order do you punch them in? That's important, obviously, to use the tool correctly, the tool of the calculator. But I want to absolutely minimize the distraction of these keys. I much would rather have you focused on the formula, on understanding how we get the numbers, on understanding what we're trying to calculate. And putting this tool into our hands distracts us from that. In college level math, including at Edmonds College, the teachers there in the beginning classes of college level math, they will teach you everything you need to know about using a graphing calculator. They do not assume that you've used a graphing calculator correctly in high school, so you won't be behind. And then you will have a little bit more foundation and a little bit more understanding of what the numbers are doing, so that hopefully learning how to push the buttons will not distract you. But right now, I consider those buttons a distraction and a pain in the butt, honestly. It's better just to do it this way on the paper where we can see it and understand it. And so I don't want to do the graphing calculator problems. The end. Goodbye. Okay, that is the end of lesson 114. I wasn't joking when I said it was the end. That is a very hard lesson, and we're going to come back to it next year, so don't be sad. Okay, bye.